All right, thank you very much. So the first speaker of the afternoon is Mike Piscopo, and he'll be speaking on SDRs on GPUs, practical OpenCL blocks, and their performance. And I'll just hand it right over, and thank you very much.
Thank you, Derek. All right, so I've never been accused of speaking too quietly, so hopefully with the mic it's not too loud, but if you can't hear me, let me know. So real quick, you guys are probably like, I've never heard this guy's name before. Who is he? My name's Mike Piscopo. I'm the Director of Technical Consulting Services at a company called Delta Risk. My team's primarily responsible for doing penetration testing in a more traditional cyberspace, so internal, external, wireless LAN, web applications, and lately in the past year I've picked up product development as well. So none of that quite sounds like SDR, but I got introduced to SDR about 4 years ago. I got a guy on my team, and a young guy, and he comes in and he goes, oh, well, we're doing all this hacking work. Have you ever heard of SDR? Have you played with it at all? And I went, no. He's like, yeah, it's great. You can work with air traffic signals and pagers and car remotes and all kinds of stuff. And I picked it up, and it's kind of turned into a hobby or obsession ever since. So I think one of the things that I like about it is that it kind of plays to some of my past lives. So I know there's a Virginia Tech contingent here. I'm a former Virginia Tech grad, aerospace engineering, and I started out of college working for an aerospace contractor, and we were working on all kinds of projects, including like distributed centrifuge systems, where we really had to pay attention to data acquisition and frame rates because we had people in the loop. So it was really important to make sure we had things under control, and then later on, doing various embedded projects and application development before moving on to IT and eventually security. And over the winter break, I had some time, and like everybody else, you pick up your hobby, right? So I went back to doing some SDR work. Aerospace background, of course, satellites are always of interest, and I was working on some things with some very weak signals. Got frustrated with antennas. I hate antennas, by the way, if there's antenna guys in the audience. But I started to think about some of the high-speed bandwidth that the satellites were pushing towards, and you start to look at things like 100 megs a second, or even try to push faster than that. And so it started to cross my mind, well, from an SDR perspective, could we even process things that fast? If I wanted to try to push a 60 meg, 100 meg, or a 250 megahertz wide signal, could I actually even process it? I mean, I've got a computer in the loop, right? And so because this was more of a hobby and I don't have expensive hardware at home, and I'm looking around what I've got a ton of graphics cards sitting around. I've got a NVIDIA 1070. My kids just got a VR system for Christmas. They've got a 1080 card that they refuse to let me steal. But you start to look about this, and even in cyber, we use these GPUs all the time. For password cracking, we've got a box in our office. We'll jump 3 GPUs in there, and we can crack passwords that might take months to crack, and we can do it in a matter of days. So I decided the antenna thing was a little bit out of my skill set, maybe a little harder than I wanted to tackle. OpenCL and getting things working on GPUs plays a lot more to my background. Let me take a look at it. And so before I went back and I reinvented the wheel, I started to do some Googling and said, let's see if anybody else had done this. And so there's a lot of good research out there. And there were a couple of proof of concepts, but nothing like what I was really looking for, right? I mean, I really wanted to say, all right, I want to know OT module. I don't want to have to know the details. I want a GPU accelerate my flow graphs. I want to grab a block from the right. I want to drop it on my flow graph, and I just want it to work, right? And so that kind of gave birth to what I was calling the CL-enabled project. And I worked with a number of the folks here to make sure we've got the project up in PyBombs, and it's up on GitHub. So it's completely open source. It's out there for all of you to use. And once I decided that in a moment of weakness, I said, maybe I can take this project on. Let me see about doing it. And they say about raising your hands, right? Never volunteer. So I kind of took a step back, and I said, all right, well, let's take a look at requirements. What do I really want to do? And I got to be the user on this side. So I said, all right, forget about how hard this is going to be. What do I really want it to do? And I said, if I could take all of the basic components I use in my flow graph, so that's signal sources, it's multipliers, it's filters, and because I was kind of focused on digital communication sides, all the blocks that might be involved with just sort of baseline DMOD, right? So amplitude, phase, frequency shift decoding. And then opportunistically, any other blocks that I came across along the way that seemed like I could do them relatively quickly, it'd be nice to have some of those kinds of things. And then from a scalability perspective, again, I was looking at a box. I had some 730s sitting on the ground. I had a 1070 in the box. It'd be great if I could use all of them, right? If I could get 2, 3, 4 GPUs in a box let's throw them all at my flow graphs and let's see what we can do. So scalability was something that I was thinking about. And so because you may have different cards of different capabilities, it'd be nice to kind of have my more intensive ones running on the better cards. Maybe something that's just sort of a little accelerated, but it would run fine on a lower end card. I want to be able to assign things to the cards that I have at my disposal. And then the question came up, well, if I want to accelerate it, that means I need to know if it's running faster or not, right? So I need to be able to measure this stuff. So, can I actually hit 60 megasamples per second? Could I even clock it just on the computer side of things, 250 megasamples per second if I wanted to go that high? Would it even work? So which meant I had to build in some things into the project to do various tools for timing. And then I decided, well, let's take a look at this from a little bit different perspective. And let's take a look and see if we could take these blocks and say, all right, which ones are accelerated? Which ones really always run faster than the CPU? Which ones are kind of close, and we'll call them offloaded? And then which ones, they run OK, and they may be good enough. They may be above our threshold that we normally pass samples at. But if we're trying to really push speed, they're not faster than the GPU ones. And then extensibility was the other side of it. I said, well, I don't want to have to go back and recompile code every time. And there's probably a lot of folks here that aren't necessarily C++ developers. And you guys probably don't want to have to recompile code all the time, too. So it'd be great if I had some blocks where I could just throw some general purpose kernels at it. And it was a lot less effort to get started. And that formed the basis for getting this project going. So this list that you see up there, and I'm not going to read it off. You guys don't have to memorize it. But this was the list of blocks in the GNU Radio framework that I tackled. All of the ones that are highlighted in red are the ones that actually did pretty good. They were either accelerated and really beat the CPU, or they were offloaded or maybe a little bit accelerated if you messed with the buffer sizes a little bit. Filters were a little bit of a surprise. They're kind of a gray area, and you'll see from some of the charts later on with some of the block sizes and the filter sizes. Sometimes you can offload them, and they'll work fine depending on your sampling rate. Sometimes they're not faster on the GPUs. And of course, the custom ones you don't know until you write them, right? So before I get too far into the performance, I thought, what makes an algorithm a good algorithm? And just a real quick overview on some of this. I promise I'm not going to get too math or too developy here on you guys. Once you get a look at this, you'll see why in the graphs going forward, some of this will start to make sense. So when you look at doing GPU acceleration, it's really looking for data parallel processing. So it's looking for single instruction, multiple data points running simultaneously, and it really likes doing what they call atomic calculations. So if you look at the little color blocks on the side, you get A1 plus B1 equals C1. A2 plus B2 plus C2. You can run all those in parallel. There's no dependency on them. That kind of stuff runs great, right? If you start to have to get into some practical things where you got to write some if statements and maybe make some logic, it's a little suboptimal because the way that the engines work is they'll kind of wait for everything to get on the same instruction, and then they'll do that. So it's like everything has to be on sine or everything has to be on cosine. The tough ones are really the ones where you get these rolling sequential calculations, right? And it's just a fictitious example, but if you can't compute n plus 1, so you compute n, there's no way to kind of tell it to do all of them at the same time. And those are the ones that kind of fall down when you're starting to look at this data parallel processing. The bottom example, the quad DMOD code, if you look at that, that's a great example of something that you can do in parallel. There's no interdependencies on it. You can blast that out and run them all simultaneously. And hopefully, and we did get a good bit of acceleration out of that one. So this was probably the only one that I was a little bit disappointed with, and that was getting into some of the costless loop stuff because there was so much feedback and control going on, which of course is as expected. But you could see some of the errors. This is why it was hard to parallelize this. So if you expanded and flattened the loop out, you got all these things where you got to do a bunch of things before you can calculate the next point. And I did try it just to satisfy my own curiosity in what they call task parallel processing mode. Performance was absolutely horrible. I mean, it dropped to about 715K per second. I'm like, you can't even really use that. So something for the audience. If there's anybody here that's better at this math than me, and you guys have some good ideas on how to parallelize this, please catch me afterwards. I'd love to give it a shot. But this one was one I really had a tough time with. So what I found with the OpenCL version of all the code was the one thing that really made a difference in terms of whether or not things ran faster than the CPU or not was the data copy process. And so when you're working within a box where you go right from the ADCs into FPGAs and things like that, it's great. You don't have to worry about this. But when you get into a general purpose computer and you're working with PCIe card, now I got to move the blocks of data I want to process to my GPU, and then I got to get them back. And so when you do that, you do pay a transfer cost. And so when you look at the cost of doing any of these functions just on the CPU, it's just really running the function. And if you're using Volk or any of the SIMD capabilities in that, it kind of makes it even harder. But for the GPU, it's really the sum of the cost of getting it there, doing the processing, and then copying it back. And so you can play some games with it. The more data you throw at it at one time, the better performance you get out of it. Or if you start to bump up the complexity in the calculations that you're doing. So if all you're doing is add and subtract, you're probably going to get killed moving the memory around. But if you start to get into things like log functions and trig functions, now the cost of the memory transfer can be offset by how long it takes to process on the GPUs versus processing on the CPUs. So if I had to kind of boil it down, of course, the engineering side of me likes equations, right? So if I had to kind of boil it down to one formula, you take a look at the block size and what you're doing, it really kind of boils down to, if you take a given block size, the cost of the time to get it there, the cost of the time to process it, and the cost of the time to get it back. As long as you keep that less than how long it takes to run on the CPU, then you're in pretty good shape, and you're probably going to get some good acceleration out of the GPUs. So testing was important, and I felt like I was back in a college lab, right? I said, all right, if I'm going to do this and I'm going to write anything up, it's got to stand a peer review. And we all hate that, but I said, let me put some structure around this. So I ran a couple different tests on a couple different platforms and things I had laying around, right? So I had a new card, I had a 1070, I had another older box that had a GTX 970 in it, I had my laptop that had an NVIDIA 1000M in it, and then just because OpenCL's multi-platform and you can run on CPUs or GPUs or OpenCL-enabled FPGAs, I said, let me run it on a CPU version 2. Just to make sure there's no bugs or gotchas that might show up when I'm working in this mode. So the thing that you'll see in the stats and the graphs that we start to go through is to remember that the block sizes you see are the actual block sizes I processed. And so if you go and drop these into a GNU Radio graph, one thing to remember is the scheduling engine's probably not going to pass at that default buffer, right? You're going to get maybe half somewhere in there. So you may need to, if you're looking at these graphs and you go to drop some of these blocks in some flow graphs for yourself, you may have to tweak the buffer sizes if you're really messing with the performance. So keep that in mind. And also, the way I did the timing tests, I wanted to take all the other moving parts out of it. I wanted to isolate it and say, all right, is my function really faster than the CPU function? So what I did was I just timed the work function calls, right? So I just timed the CPU-only versions, and I just timed the GPU codes. So hopefully taking a little bit of the moving parts out. So with that said, I can't say for sure that the numbers you see, take these as a theoretical maximum, right? When you start to jump it in and the scheduling engine's doing its thing and you got all kinds of other things going on, you could get a little variations. But I figured if I couldn't beat it here, there was no way I was beating it in the flow graph. And the other thing is, I did build in the tools, so you'll see a number of tools in the OOT module. So there's everything starts with test. There's a CL-enabled version that'll provide timing. There's one for filters, and then there's one for the custom kernel. And again, this is all available for you guys to download and play with. Another thing that I learned along the way is what they call fused multiply access, or fused multiply add. And so it's just another way to accelerate some of the processing. Some GPUs have it, some don't. So when I wrote the kernels, I tried to take advantage of everything that I had, and some of them will use that as well. So just kind of starting to get it. There's a paper that I submitted for the conference, and it's got every one of the blocks that we had up there. There's charts like this for every one of them, and we'd be here for a couple of hours, and you guys would probably get bored listening to me. But I just picked a couple of the highlight ones here. So if you want to see the details for each of the blocks, go and take a look at the paper. But this log 10 one really kind of exemplifies what I was hoping to see across the board. So if you look at the different block sizes for the ones running on the CPUs, they're all kind of flat along the bottom. And the red arrows on the left-hand side give me two metrics. It's the 60 megasamples per second. So if you think about that's kind of what most of us are probably buying off the shelf with some of the low to mid-grade stuff. And then the top one was a 250 megasamples per section, which was kind of more of a wish item, right? But you can kind of see where some of these things fall in. And the CPU ones make sense, right? If I pass it twice as much data, the CPU doesn't change. It's going to take twice as long to run, so the actual throughput looks flat. When I got into the GPU side, another thing happened that was as expected, right? The better cards ran better, right? So the laptop one kind of ran at the bottom. The 970 was in the middle. The 1070 was the best. A couple little variations. In the CPU one, you can see all kinds of little anomalies probably with how OpenCL manages the CPU code. So it was up and down, and it wasn't a total surprise. But you can start to see how some of the performance let out. And the GPUs always beat the CPUs. Great. So if I could have that across all of them, that would be great. Wasn't quite the case. Quad DMOD was another good one. I tagged this as sort of offload, but just with a little block size tweak, it generally performed better than the CPU equivalents. But you can see it's kind of like back to economics, right? There's always these trade-off points. And where the crossover happens for the GPU versions to be faster than the CPUs varied depending on the CPU and the GPU that we were using. So you can see for the 1070, it was 8 or 9K kind of block sizes, transferred pretty quick. But I mean, you can see how high the throughput is on these algorithms. And just a note, even if they don't beat the CPU, if you look at the throughput numbers that we're talking about, any of these blocks, other than the costless loop one, but I mean, you can really drop any of these blocks into a GPU. And if you're running at 60 megasamples per second or lower, they're going to perform better. You can offload as you need to if you want to take a block and throw it on a GPU or a couple GPUs and then use the CPU for other things. So if you've got a flow graph where you're really pushing it and you want to get a couple things off, this is definitely an option. Signal source was another one, another core component. You see it in a lot of flow graphs. And the same kind of thing happened. You get this trade-off point where you get to a block size where the GPU starts to surpass the CPU. But again, you can see the arrows on the side. The bottom one's the 60 megasample per second, and all of them were well within what you'd probably be working with in most of the flow graphs. So this was an important note. And yeah, I really intended this to be something. I was hoping when I was looking for this that somebody had already done this work for me, right? And I didn't want to have to, when I got this together, say, all right, well, this is just mine. I wanted it to kind of give back and release to everybody else. And so my intention is that if there's folks that have a direction they want to go with some of this, by all means, and if you need to, reach out to me. I'll see what I can do to help. But on the functions that had the trig functions, if you start to get into playing with your own kernels, one thing that I ran into, and as Ben said with our program, I ran into the same thing with the paper. I forgot to make a tweak in the signal source section of something that I had fixed. But when I first put this block together, you'll see on the chart on the left, I figured my benchmark, at least to start, was this. If I take what I did and overlaid it on top of the GNU radio block, if I didn't get an exact match, then something was still wrong and I still had some more work to do. And so when I did the signal source one with the trig functions, I got the plot on the left. And like any good developer, the first thought was, I did something wrong. Let me go back and figure out what this was, because I spent some of the time writing this code. It was in the morning over coffee or on the weekends. And so this was probably something that I did. Well, when I dug into it a little bit more, in the OpenCL spec, the way that they flag the trig functions is that the precision is implementation specific. And I did see that. Sometimes they were only running out to 9 decimal places. Some of them, I think on the CPU, I was only seeing it out to 6. And because of that, it was wreaking havoc with my trig functions. So what I ended up doing was going back and just doing the calculations with double precision. And as soon as I did that, it flattened right out. The other good thing that happened with that, though, was if you look at the native block, it uses a lookup table. And there's this just little anomalous spike, really low noise that shows up just with the native block. And so with the pure trig functions on the GPUs, not only are they faster, but I noticed that secondary spikes kind of went away. So I think in the context of really getting a true pure tone out of these signal sources, the full trig functions on the GPUs did a really good job. All right, so filters. This one was a little bit different than what I had expected. You hear everybody talk about how great GPUs and things like that could be for signal processing. If you look at the gold circled block there, that was the best CPU and the best graphics card that I had, right? So that's the 1070. And so what I found was there was something going on, whether I did it as a time domain filter or a frequency domain filter, I just couldn't beat the CPU. It doesn't mean that it's unusable, and the red bars there kind of vary. It brings the bar down a little bit. So if you look at like a 10 megasample per second and a 60 megasample per second, they're still usable, but I was a little disappointed I didn't quite get the throughput that I wanted to out of it. And if you think about what the cause of that is, if you go back to the performance killers, what really ended up happening here was there was this time trade-off. For low tap rates, the time domain filters are faster. So as the tap rates start to go up, the FFTs get faster. But when you do the FFTs, you got to do 2 moves to the cards. You got to do one to convert it in, do the taps, and then convert it back. And those 2 memory moves just absolutely killed the performance on the FFT filters. So the thing was the CPU algorithms were just so fast, it couldn't touch it. So a couple takeaways here. There are a lot of good blocks that are in this project that you can drop into any flow graph. What you may want to do, I know I've had folks reach out to me with all different kinds of graphics cards, and that's kind of why the test tools are there. If you want to play with it, go ahead and run the test tools, the command line tools that come with it. Take a look at the throughput that you're getting. Again, as long as it's above the threshold for the sampling rate that you're going to have, they're absolutely usable blocks. My recommendation is to try to pick the most expensive block you got on your graph and drop that one as an OpenCL. Again, if you've got a flow graph and you want to do more than one GPU block, if you try to do more than one GPU block and just drag them over and run them, you're going to take a performance hit for it because each of the blocks is trying to get exclusive throughput on the cards, right? And it makes sense. You're going to start fighting over resources. So use multiple cards if you want to. Works great. There's another command line tool called CL View that's included with it that you can kind of get the numbers out. And when you go into your flow graph, there's just little drop lists you can kind of fill in and say, I want this card number. And you can drop them in that way. Again, we did see that the signal source had a little bit purer waveform, which was kind of a nice outcome. And then if speed is your absolute goal, you go for speed for 2 reasons, right? You either want to do more with less, so you want to run things on maybe lower end hardware and not have to take such a processing hit for it, or you really want to push the throughput envelope. So some of the things that after I finished this project up, I started some sister projects. Things that frustrated me, like the Costas loop that I couldn't speed up. I took that and a few other things, put them in this GRLFast project that's up in PyBombs too that you can download. And just went back to some core CPU optimizations, taking out virtual pointer jumps, doing some code optimizations, pulling in the fuse multiply adds where I could. And I ended up getting about a 60 or 70% performance increase on the Costas loops over there. But some other things that you can do. If you're trying to get around DC spikes, which was a problem when I first started with GNU Radio, there's another sister project called CorrectIQ that has 3 different options where you can kind of filter that out. But if you do want to do it, even with the GPU accelerated versions, you can use the signal sources and offload that whole processing piece and take care of that. And of course, spreading out the work is always a good idea. Back to my IT roots, if you split your presentation layers and your business layers out, if you do some of this hardcore decoding on one system, you can always use something like network syncs. Feed it off to another block and do your visualization pieces there. Because even if you like using things like GR-Phosphor and you look at the OpenGL, and from what I learned about the FFT transforms, doing the OpenCL offloads for those FFTs, you could still take a hit for it. So take that off and feed that off to another system. And I did it, guys. I tend to talk a lot, and I was worried about hitting an hour's of content in a half hour, but I do have a couple minutes, it looks like. So if you guys have any questions, I'm happy to take them.
I've got probably 10,000, but I'll boil it down if you let me have 2 questions. One, have you tried using CUFFT?
I was looking at that, and I ended up going with the CLFFT library.
It's going to be more generic, of course.
Yeah.
That'd just be interesting to see. Okay. 2, have you looked at pushing the data down into the pushing the data down and leaving it down there, and then looking at the performance if you've got from one block to the next, and then you use the blocks just to pass triggers?
Yeah. So there was some good research that I found where they'd done some custom buffers that they could pass along the blocks like that. And there is one block that you'll see that's called an SNL helper, and I did just that within the block. I kind of did it all in one time.
I'd like to see that.
But I think you got 2 options with that. First is if you feel like taking on and doing just a custom C++ class there, and there's a good framework base class that you can build off of, you can just kind of, depending on what you have to do, hold the buffer and then pass it to one kernel and pass it to the other kernel, or you could just write one kernel that'll do it all. The only time you'll have to come back out to the CPU is if you start to hit blocks where you got to do some of those sequential calculations. So if you got to hop back out to an AGC block or a costless block, you'll have to pop back out. But other than that, as long as the algorithms support it, you can stay down.
Absolutely.
Yeah, Jose, could you please?
I think I might have missed a little bit in the front, but let me ask a question.
Hang on.
Did you change anything on the CPU multi-core compile time settings? Did you play around with that?
Nope, didn't do any of that.
Thanks.
Yeah, I had a question about the GRL fast. I haven't looked at it, but are those CPU optimizations like specific to a certain CPU? And
Nope.
if not, wouldn't that be like a great candidate to upstream into GNU Radio Core?
Quite possibly. If you guys want to catch me afterwards, I'd happy to talk about it. The costless loop in particular, I know what the big performance hit is, so if anybody's here that maintains it, catch me afterwards, and I'll let you know what I saw. But yeah, the FMA capability, I think it's with the SSE 3 on the CPUs, and so if you get any modern CPU, they should support it. You just got to do some logic in the code to decide if it's there or not, and then you can use it. But yeah, you can work that back in.
Could I get the next presenter, please? I know there's been a substitution. Thanks.
One more question? So this is kind of just piggyback. You didn't use OpenCL pipes at all? So in 2.0, they actually have defined methods of chaining together blocks,
I
and
thought
passing
about
data
it.
back and forth without going to the host.
And I started to look at playing with some of that stuff, and as soon as I started to think about getting down into 1.2 and 2.0, taking care of using some of those other features, I didn't want to rule out folks that had other cards. Like I had somebody that reached out to me this past weekend that had a 970 card, and they're like, it only supports 1.1. So I was trying to stay away from that just to make it a little more broadly accepted.
And do we have one last question? Seeing none, thank you very much.
And thank you for your
Thanks.
presentation.
Yep.